So we have stated the principle of minimum potential energy in the last class. So I did not give the proof, so today I will present the proof of that theorem. But first let me just state that theorem again. So we said that phi of u is equal to minimum over v of phi of v, where this phi of v is equal to half of integral of epsilon of v times c times epsilon of v times d omega over omega minus integral of rho v dot v times d omega over omega minus integral of v dot d bar times d gamma over gamma t. So last time I think I had written it as phi of u instead of that, but since here there is phi of v, I have written it in the form of phi of v here. And so if you minimize this potential energy functional over all kinematically admissible fields v, then the minimizer is u, that is the actual solution of the problem. Okay, so one important thing to note here is that see this potential energy function is a completely artificial function in the sense that it does not have any physical interpretation. It has the same units as energy, and so we call it as potential energy. But you have to remember that basically it does not have a physical interpretation like kinetic energy, or when we say potential energy like mgh and things like that. So this does not have any physical interpretation, although we still call it as potential energy. So this is just a mathematical function whose minimizer is the actual displacement u among. So if you minimize it over all the kinematically admissible fields, so last time we saw that the kinematically admissible fields are the ones where the v satisfies the condition that so basically v is equal to u bar on gamma. So these are all the fields which satisfy this condition on gamma u. So let us prove this particular theorem. So let me write g of alpha as equal to pi of u plus alpha z. Okay, so this where this v satisfies this, so let me call this v as equal to u plus alpha z, and v is equal to u bar on gamma u. So basically z is equal to 0 on gamma u. So this alpha z you can think of as like a perturbation on the actual solution u. So this g of alpha I can write as equal to phi of u. So you substitute now this u plus alpha z, you substitute now in place of this v here. So you will get epsilon of u plus alpha z, and here also you will get u plus alpha z, and then use the linearity, right? So because epsilon of v is a linear operator, so that in the sense that epsilon of v1 plus v2 will be equal to epsilon of v1 plus v2 will be equal to epsilon of v1 plus epsilon of v2. Correct? This is because this is a linear strain measure. It's a linear operator, and so you can use this linearity to expand this out, and then you will get whatever I am writing. So this is plus alpha times integral over omega of epsilon of z matrix inner product C of epsilon of u times d omega plus minus integral rho z dot b, this is over omega, minus integral of z dot t bar d gamma over gamma t plus alpha square by 2 integral of epsilon of z times c times epsilon of z times d omega over omega. Yeah. So after expanding out So if you substitute V is equal to U plus alpha Z and expand out this whole expression, then this is what you will get. So we have used the fact that Z is equal to 0 on the boundary gamma U here. Okay, so this is what you will get. Then now you want to minimize now. So since U is a minimizer, so since U is a minimizer, so first we are assuming that this minimizer holds. Okay, so since U is a minimizer of pi of V over all V, we will get that dg by d alpha evaluated at alpha equal to 0 is equal to 0. Right? So that is just the first order condition for optimality of a function, right? So if a function is a minimum, right, the derivative vanishes, right? So that is the necessary condition. So dg by d alpha evaluated at alpha equal to 0, because see, you have to evaluate it at alpha equal to 0, because when you evaluate it at alpha equal to 0, you will get u, and so the minimizer is at u, right? And so hence dg by d alpha evaluated at alpha equal to 0 is equal to 0. So if you now differentiate this function with respect to alpha, then here you will get an alpha, and then when you evaluate that at alpha equal to 0, this term will vanish, and then if you differentiate this with respect to alpha, that is just going to be 0. If you differentiate this with respect to alpha, whatever is in the brackets, you will get that. So you will get that, so this implies that integral of epsilon of z times c of epsilon of u times d omega, this is over omega, is equal to integral rho z dot d omega. Here I think there should be a d omega here, d omega minus plus z dot t bar d gamma over gamma, and then z is equal to 0 on gamma, right? So that is exactly the variational formulation. I may have used a different symbol, I may have used V when I did the variational formulation, but it is essentially the same thing, right? So here this Z is the variation now of U, and so we get back the variational formulation, right? So, but if you read the statement of the theorem, then we have said that converse is also true. So that means if we start now with the variational formulation, then we get back the statement of the minimization problem. That means over all kinematically admissible fields V, the minimizer is the actual displacement U. Correct? So that also we need to show it. Fine. So let me raise this particular font here. So now converse of the theorem. So conversely, if the variational statement holds, so that means then in that particular case, this whatever is there in the brackets is equal to 0, because that is the variational statement, right? So then you will get that g of alpha is equal to pi of u plus alpha square by 2. See, now because this whole bracketed term vanishes, and then only this term will remain. So plus alpha square by 2 integral over omega of epsilon of z times c times epsilon of z times d omega. Yes, and then now you see that we assume that this c is positive definite, right? So that was the definition that I had given just before we started the discussion of this principle of minimum potential energy. So since now this c is positive definite, definite. So that means this whole integrand is going to be positive, correct? Because C is assumed to be positive definite. So this integrand is positive, hence the integral is also positive, right? So hence we get that G of alpha, so that is which is equal to pi of u plus alpha z is greater than or equal to pi of u, because this whole term is positive. So it can be 0 also. When alpha is equal to 0, then it can be 0 and then you will get equality, right? And so this is always greater than or equal to pi of u with equality when alpha equal to 0. With equality if alpha equal to 0. So you can see that basically the minimizer is the actual displacement u, correct? So that is so that shows that the potential energy is a minimum when V is equal to the actual displacement u. So if you minimize this potential energy, so I'm just summarizing. So basically you take all kinematically admissible fields V, then you minimize the potential energy over all these kinematically admissible fields V, then the minimizer of that potential energy is the actual displacement u. Okay, so that is exactly what we have got now. Right? So this is so that proves now the principle of minimum potential energy. Fine. Then we will go on to the next theorem, which is the Clapharon's theorem, work theorem. So that is this is also a very, very important theorem. So let us look at that now. Yes, so let us look at Clapharon's theorem. So this theorem basically states that 2 times the strain energy is equal to the work done by the loads. Okay. So in the 1D context, let us just try to explain this. Suppose if this is your stress strain graph, right? And then so this area here is the strain energy, that is integral of epsilon times tau, that is the strain energy, and then 2 times the strain energy would be this whole rectangle, and so the area of this rectangle is equal to basically the work done by the loads. Okay, so let us try to show this particular theorem here. So if B is the body force, so remember that all these theorems hold only for the static case. So we have not, basically we are ignoring all the inertial effects, like acceleration we are just setting to 0 in all these theorems. So if B, so even in the theorem of minimum potential energy, that also was for statics. This particular theorem is also for statics. Okay. So if B is the body force, and T is equal to tau times n, is the traction, on gamma, then 2 times u of epsilon is equal to integral rho b dot u times d omega plus integral of t dot u d gamma over gamma. Okay, here one important thing to remember is that this is an integral over the entire gamma, not only on the part where the tractions are prescribed, but on the entire boundary. So here let me just draw this. So suppose if I draw the whole boundary here, so part of it is gamma t, and then part of it is gamma u, where the displacements are prescribed, and so this is the entire boundary. So that means this gamma is equal to gamma t union gamma u, the whole boundary here. So you have to take a traction even on the part where the displacements are also prescribed when you do this thing. And this u of epsilon here, u of epsilon is equal to half of integral of epsilon of u times c times epsilon of u times d omega over omega. So that is just the, so this is the total strain energy, then 2 times the strain energy is equal to the work done by the loads. Okay, so this is the theorem. So let us try to show this. So let us start with the right hand side. So RHS, so proof of this particular theorem. So RHS is equal to integral of rho v dot u times d omega over omega plus integral of tau n dot u times d gamma over gamma. Right? So this, I am just using the Cauchy relation, that traction is equal to now. And we can then write this as, so this, just take this particular term. This is n dot tau transpose times u. Okay? And then I can apply the divergence theorem to this one. So this is equal to integral of rho b dot u times d omega over omega plus del dot tau transpose u times d omega. So transformed it from a surface integral to a volume integral, and then now you expand this out. So this is the usual, use that initial notation and then you can simplify this particular relation. So this is equal to integral of u dot rho times b plus del dot tau plus integral of tau matrix inner product del u times d omega over omega. And now this is equal to 0 because del dot tau plus rho b is 0 by the balance of linear momentum. And so this is equal to integral of tau matrix inner product del u times d omega over omega. And because tau is symmetric, we can write this as tau matrix inner product half of del u plus del u transpose. Right? So this is the one of the homework problems. So this is tau half of del u plus del u transpose, and this is equal to integral of tau times epsilon of u times d omega over omega. So this so that shows that this is equal to twice the strain energy. So this here is the strain energy. Right? So this is nothing but the strain energy, and so this twice the strain energy is equal to the work done by the loads. Okay, so that is theorem here. Fine. So so let us just contrast between the principle of minimum potential energy and this Clapharon's theorem. As I said that in the principle of minimum potential energy, that potential function pi, right, that is just a artificial mathematical function, right, and if you minimize that artificial mathematical function, then the minimizer is the actual displacement u. Whereas in this particular theorem, all the quantities that are involved are physical quantities. Okay, so that is something to remember here, that these are all the, these involve the actual displacements, the actual strain energy and so on. So even in the principle of virtual work, right, or the weighted residual method or the variational formulation, we have seen that that also involved artificial quantities like the variation, right, that means the perturbation of the displacement field. So that was also a purely mathematical concept, right. So both the principle of virtual work and the minimization of potential energy principles involved some artificial functions, whereas this particular theorem is totally in terms of physical variables, that is actual displacements and so on. Okay, so this is the theorem here. Fine. So now we are going to talk about the uniqueness now of solutions in linear elasticity. And so fortunately, it turns out that not only does the solution exist to the linear elasticity problem, but also it is unique. In the case of a pure traction boundary value problem, the strains and the stresses are unique and the displacement is unique modulo a rigid displacement. And in the case of a displacement boundary value problem or a mixed boundary value problem, all the three fields, that means the stress, strain and the displacement, are all unique. Okay, so we will prove this particular theorem of uniqueness. So this is a very useful result. So I will indicate in what way it is going to be useful. Yes. So uniqueness of solution. So assuming C, that is a constitutive tensor, to be symmetric and positive definite, the displacement and mixed boundary value problems have a unique solution for U, epsilon and tau. So these are the three fields, right? This is the displacement field, the strain field and the stress field. So all three are unique if you have a displacement or a mixed boundary value problem. And in the case of the pure traction boundary value problem, in case of the pure traction boundary value problem, the epsilon and tau are unique, while the displacement, solution is unique modulo infinitesimal rigid displacement. Small rigid displacement. So basically, what do we mean by this infinitesimal rigid displacement? So that we have seen that epsilon equal to 0 if and only if u is equal to w times x plus c. Correct? So that we have already seen. And so what we mean by this infinitesimal rigid displacement is this particular path which leads to zero strength basically. So, so what that means is that if suppose U1 and U2 are two different solutions, then they will be separated by this W of x plus c basically. So the displacements are not unique, but the strains and the stresses are unique when you have a pure traction boundary value problem. So I think in the last class, I think I had already explained this particular thing, right? So suppose I indicated this. So suppose you are applying some traction on the on one face and an equal and opposite traction on the other face, so that this body is in equilibrium, right? And then now you can see that I am translating this, or I am also able to rotate it, right? So this basically corresponds to this Wx plus c. So the displacements now you can see are not unique, right? I can just move this whole body, right? And it's a pure traction boundary value problem because the tractions on these lateral surfaces are 0, and then on the left and the right faces I am applying some tractions. And so this is a pure traction boundary value problem. As you can see that the displacement is not unique, but the strains and stresses that are generated now within this particular body, they are unique. Okay, so I think I have explained it. So now if you impose a displacement constraint, right, suppose if you fix this particular boundary, then you can see that now it cannot move the way it was moving, right? And then the displacement also becomes unique in that case, or even in a mixed boundary value problem, or in a prescribed displacement boundary value problem. The rigid displacements are basically eliminated, and then you get a unique solution for the displacements as well. So that is the statement of this particular theorem. Okay, so let us prove this theorem. So proof of this. So before proving uniqueness, actually one should always prove existence. So that is very, very important. See, suppose if there is no solution that is existing, then it is pointless to try and prove uniqueness of a solution, right? So proving existence of the solution is an extremely hard problem. Okay, so it involves very elaborate concepts from functional analysis and so on and so forth. So we will not get into that. Okay, we will simply assume that a solution exists. But as I said, that mathematicians have already proved that a solution exists to this particular problem. So we will assume that a solution exists, and then we are trying to show that the solution is unique. And typically the strategy for showing that a solution is unique is that we assume two different solutions and then show that the difference between those two solutions is 0. That is the typical way we show uniqueness of solutions. So let epsilon 1, let u1, epsilon 1, tau 1, and u2, epsilon 2, tau 2 be two solutions. That satisfy the governing equations and boundary conditions. Then let u tilde be the difference, u1 minus u2, epsilon tilde be equal to epsilon 1 minus epsilon 2, and tau tilde be equal to tau 1 minus tau 2. So this tilde, u tilde, epsilon tilde, tau tilde is simply the difference now between these two solutions. So we want to show that epsilon tilde is equal to 0 and tau tilde is also equal to 0, right? That's what we want to show. So that will show that the solution is unique. Okay, then now we have that del dot tau 1 plus rho times b is equal to 0. Del dot tau 2 plus rho times b is equal to 0. So if I subtract this, I will get that del dot tau 1 minus tau 2 is equal to 0. Right? And so this implies that del dot tau tilde equal to 0. Correct? And then similarly, you will get that epsilon tilde is equal to epsilon 1 minus epsilon 2 is equal to half of del u tilde plus del u tilde transpose. See, this is because all the operators are linear operators, right? So this, for example, would not hold with the green Lagrange strain, correct? So then, of course, such relations, then once you have a nonlinearity in the strain displacement relations, this will not hold, right? So here, because of the linearity of the operators, you will get that epsilon 1 minus epsilon 2 is just this half of del u tilde plus del u tilde transpose divided by 2. And then the constitutive relation will be again tau tilde is equal to C times epsilon tilde. So remember that we do not have a B1 and a B2 because it is assumed that the body force is given and the tractions are given, and then we are trying to find out that under the given body force and under the given traction whether the solution is unique or not. Okay, so that's why we are putting these subscripts 1 and 2 only on the displacement, strains and stresses and not on the body force, because that is assumed to be a given function to us. Yes. Now let us use, so you can see that basically these tilde, whatever tau tilde, epsilon tilde and u tilde, they satisfy the usual equations of equilibrium with a body force of 0, correct? Because so effectively it is like a body force of 0. So I am not saying that the actual body force is 0, but these tilde fields are satisfying equations which have a body force of 0. Okay, so that effectively it is like a 0 body field. So, so let us use this Clapharon's theorem now for this tilde fields now, and then see what you get. Okay, so okay, so then by let us just see. So this u tilde, epsilon tilde, tau tilde obey the usual equations of elasticity with 0 body force. 0 body force. So as I said, actually the body force is not 0, but in the mathematical framework, this u tilde, tau tilde and epsilon tilde satisfy the same equations with body force 0. So that is what we are saying. And then by Clapharon's theorem, so by Clapharon's theorem, you will get that integral of t tilde dot u tilde times d gamma. This is over gamma is equal to 2 times integral of w of epsilon tilde times d omega over omega. So that is because the body force is 0, so that doesn't enter into this particular thing here. And your t tilde is, so here this t tilde is equal to tau 1 minus tau 2 times n. So that is the Cauchy principle here. So that is your tau tilde in this particular case here. And so this is equal to tau tilde times n. Okay, so you get, so as I said that all the relations are exactly identical to the usual equations of elasticity now. So, so now for the displacement boundary value problem, for a displacement boundary value problem. So this BVP stands for a boundary value problem. Your u tilde will be equal to 0 on the entire gamma, because the whole boundary is has a displacement prescribed, and so u is equal to u bar on gamma u on gamma, and then the u tilde, which is u1 minus u2, since the displacement is prescribed, the u tilde will become 0, right? Then for a mixed boundary value problem, so for a mixed boundary value problem, we will get that u tilde is equal to 0 on gamma u, and T tilde is equal to 0 on gamma T. So, so now there are these two parts of the boundary, right? So one is this gamma U, where U is equal to U bar, and then on this particular thing you have T equal to T bar. But now since the traction is prescribed, you will get T tilde to be 0, because that is just the difference, right, between the two tractions, and both of them will be the same because the prescribed traction is the same on both of them. So basically what you will get that and okay, oh, we forgot to put the other, that is the traction boundary value problem, so let us do that also. So for the traction boundary value problem, for the traction boundary value problem, you will again get that T tilde is equal to 0 on gamma. Right? So basically what happens is that this particular term vanishes for all the three types of boundary value problems. So for all three boundary value problems, we will get that integral of T tilde dot U tilde d gamma over gamma is equal to 0, right? And so the right hand side is also 0. So this implies that integral of W of epsilon tilde d omega over omega is also equal to 0. Okay? And then now this W of epsilon tilde, let us look at that. So that is equal to epsilon tilde times C times epsilon tilde. Correct? So let us take it as 2 times W. So there is a 2 here. So let us take that here. And so this W of this 2 times this W of epsilon tilde is this term here. So this is equal to 2 times W of epsilon tilde. And we have assumed, so if you recall, we have assumed that C tilde is a positive definite function, and we know that epsilon tilde is symmetric, right? And so this whole quantity is a non-negative quantity, right? So since C is positive definite, since C is positive definite, this epsilon tilde times C times epsilon tilde is greater than or equal to 0, correct? And so the integrand, right, if that is greater than or equal to 0, this integral will also be greater than or equal to 0. But we have said that it is equal to 0. So that means the integrand also must be 0, correct? So this since integral of W of epsilon tilde is equal to 0. So now this implies that epsilon tilde times C times epsilon tilde is equal to 0. The integrand must also be 0 here. Right, and then now remember that what is the definition of positive definiteness? So this, since C is positive definite, this quantity will be greater than or equal to 0, and it is equal to 0 if and only if epsilon tilde is equal to 0. Correct? So let us write back here now. So since C is positive definite, this epsilon tilde times C times epsilon tilde equal to 0 implies that epsilon tilde, which is equal to epsilon 1 minus epsilon 2, is equal to 0. Okay? And so we have now shown that in all the three types of boundary value problems, your epsilon 1 is equal to epsilon 2. So this implies now that epsilon 1 is equal to epsilon 2. So we have shown the uniqueness of the strain field, right? Then similarly, we have that tau 1 now, which is equal to C times epsilon 1 is equal to C times epsilon 2 now, which is equal to tau 2, because epsilon 1 and epsilon 2 are the same, so you have equality here, and then C times epsilon 2 is tau 2. So basically now we have shown that the stress is also unique, correct? Now the only thing is that is left is the U part of this whole thing, right? So epsilon 1 minus epsilon 2 is equal to 0 implies that U1 minus U2 is equal to W x plus C, correct? Because that is what corresponds to a zero strain, correct? And so we still have this. And now what happens is that if you take a displacement boundary value problem, then basically your U1 minus U2 is 0. So for a displacement boundary value problem, it is prescribed on the whole of gamma u. So you will get that u1 minus u2 is equal to 0 on gamma. Right? And so then this implies that your w is 0 and c is also 0. Okay? And so then in that case you will get a uniqueness u1 is equal to u2 in that particular case. But if you take now, okay, so same thing happens even in the mixed boundary value problem also. So in a mixed boundary value problem, you will have u1 minus u2 equal to 0 on gamma u. And this again implies that w is equal to 0 and c equal to 0. But if it's a pure traction boundary value problem, then we cannot say that the u1 minus u2 is equal to 0, and so in that particular case you will still have this. So in a pure traction boundary value problem, you will get that u1 minus u2 is equal to wx plus. So that shows the uniqueness of the three fields in all the three situations. So just to summarize, in all the three types of boundary value problems, the strain, the stress, and the the strain and the stresses are unique. And in the case of a displacement boundary value problem and a mixed boundary value problem, even the displacement is also unique. But in a pure traction boundary value problem, the displacement is not unique. But it is unique modulo rigid displacement, right? So apart from this, there is no other non-uniqueness. So if you suppress, basically if you suppress the rigid body modes, then your solution is going to be unique. So see, this whole theorem is an extremely useful theorem. So I'll just discuss this, the usefulness of this particular theorem briefly. So the thing is that many times we will guess a particular solution, right? And we will verify that that particular solution satisfies the governing equation, boundary conditions, and so on, right? So once it satisfies the governing equation and all the boundary conditions, then it is an exact solution. So suppose we have guessed a solution and or guessed or derived or whatever, but we have now found one solution. So the main use of this uniqueness theorem is that we don't need to find another solution, correct? We need not look for any other solution. So if we have found one solution which satisfies the governing equations and boundary conditions, that's it. We don't need to proceed further, because by the uniqueness theorem, we know that that is the only solution to that particular problem. So to summarize, we just need to find one solution, correct? Exact solution. And if we find some solution that satisfies the governing equation and boundary conditions, we need not look for any other solution, because we know by this uniqueness theorem that there is no other solution here. Another important point I will note, so I think I have noted this even in the last class also, this uniqueness holds only in the case of linear elasticity. Okay, so that is because we are considering only small perturbations about the reference configuration. So we have discussed this, that our displacement vector is very small compared to the reference coordinates, and the gradients of the displacements are also small, right? So this is a basic assumption, and this uniqueness holds only in that particular case. So if you take the case of nonlinear elasticity, for example, then the solutions need not be unique. So there are lots and lots of examples of non-uniqueness of solutions in the case of nonlinear elasticity. So for example, I think I have given this example before, that if you take a column and then if you apply a compressive load, then until a critical load is reached, this will be the only solution, right? The vertically standing bar will be the only solution, but beyond a certain critical load, it goes into a buckled shape, and so that is an example of a non-uniqueness of solution. But here you can see that we are allowing large deformations, large displacements, and so on and so forth. So when you restrict the displacements only to very small perturbations over the reference configuration, then you do get uniqueness of solutions. So this falls outside the framework of linear elasticity, basically the buckling. So if you wanted to model buckling, you cannot use the linear elasticity equations. You have to go to the nonlinear equations in order to model these kind of phenomena. And similar examples, so suppose if you take a shell, for example, and then you apply a load on top of this, right, it will go into a buckled shape like this, right? So it just snaps through. And so these are all examples of, so this is known as snap through buckling. So there are lots and lots of examples of buckling and of non-uniqueness of solutions. But as I said, in this class we will not worry about that. The equations of nonlinear elasticity allow for a non-uniqueness of solution. But in this linear case, we have seen now that the solution is unique here.